So this is joint work with Yichao Zhang. And I'll be talking about this interpolation phase transition with two layers networks. And the focus is on what is called the lazy regime, and I'll explain what this is along the talk. So what are two layers neural networks? Are this class of functions? I'll try to be as self-contained as I can. Are this kind of functions? So they are composition sums of nonlinear function applied to linear projection of the data, and you combine with these coefficients AL. Okay, so it's a parametric class of function which is parametrized by this weight AL and these vectors WL. We want to use this data, this function, to fit data. So throughout the talk, most of the talk, data will be IID pairs xi yi. You have lowercase n of them, and they are IID from some distribution on RD times R. So xi, the vector xi is in RD, and the label yi is a real number. Okay, and what we want to do, we want to figure out a function f from RD to R as to minimize or to make as small as possible the test error. Okay, what is the test error? Is the expected mismatch between f of x and y on a new. You stop it. You don't hear me anymore? I see.
Okay, now I can.
I can hear you. I don't know.
Okay. All right.
Okay. Let me know because I modified my setup just before the talk. Okay, so the test error is the mismatch between a new label and f of the feature vector. Okay, so it turns out that it is often the case in modern neural networks that gradient descent algorithms actually do this by finding an interpolating solution. And here in this talk, what I mean by an interpolating solution is a function, is a two-layer neural network. So it's a function in this class such that f of xi is equal to yi for all data points. Okay, so you look at the data points, and the function is able exactly to fit the data. So the picture that you would have in mind is that the xi is here and the yi are there, and your function exactly passes through all the data points. Okay, so mathematically what this means means that you have a set of lowercase n equations, n is my set of data points, in a number of parameters, while now the parameters are the AL and the WL. So in total, you have capital N times D plus 1 parameters. Okay, so you have roughly n D parameters and lowercase n equations. And the question is, can you solve this? You try to solve this problem. So there are a couple of, a few theoretical questions that is interesting to ask. Question number one. For which triple, lowercase n, uppercase n, d, does a solution exist? This is the so-called question of network capacity. Second, can this solution be found in efficiently, and in particular via gradient descent? And third, what is the test error? So, once I substitute this interpolating solution in this test error, will it be small or large? Okay. So the objective of this talk is try to address this question in a specific context. Okay, before going there, perhaps it's good to pause a second and ask you if the setting is clear. Okay, please let me know because I cannot see all of you nodding or not. Okay, so let me start by here by mentioning little history about this topic, in particular a history of the question of network capacity. In the context of classification, okay. the constant of classification, this was, the work started, quite a long ago. So first paper to mention is Cover 1965, that basically solved the case n equal 1, so only one neuron. And then the case of general, okay, let me mention, there is an obvious lower bound. You need the number of parameters to be larger than the number of equations. So the question is really whether you can, this lower bound is tight or not. And Cover proved that in the case n equal 1, and Baum in 1985 proved this is the case for general n. Okay, so notice that the case of classification is easier, because in that case, what you are trying to do is really solve a set of linear inequalities, right? So it's kind of easier that, to try to solve this. And so these two papers give constructions of neural networks, but not algorithms. Okay, this is not really correct. They really give an algorithm, but the algorithm is not what you would do in practice. And the question was, for classification, was revisited recently by Danieli. Okay, it has two papers, 19 and 20, for n general and for gradient descent. Okay, so the two papers are under slightly different assumptions and conclusions, but okay, broadly speaking, he addresses this question. The question is much less studied for regression. So in this case, we want really yi equal f of xi. And okay, there is one main paper to mention. There is a recent paper by, concurrent paper by Bubek. Okay, is Bubek, Heldan, Lim, Kulincher, I don't know the pronunciation, 2020. And what they have is, in this paper, they have two sets of results, two types of result. First, they have a construction, in a way, a little bit reminding the construction of Baum for nd bigger than 4n and the ReLU function. The construction is a little bit, artificial. In particular, they point out that it leads to a large normal network. So probably not one that gives a good classification, generalization error. And then they have another result for nd bigger than n log 1 over epsilon. And always ReLU, I think. And this achieves interpolation up to an error epsilon. And it has a smaller norm, but there is no bound on the generalization error. I mean, no interesting bound. Okay. Okay, so this is regarding the history of this problem.
Andrea,
and yeah.
What is small and large? What do those terms mean?
Yeah, good question. Perhaps some of the authors of this paper are in the audience.
Should I try to answer?
Yeah,
so there's a natural norm, like notion of norm,
right?
Which is you just take basically the sum of L2 weights of the neurons. Actually, there is a paper by Peter Bartlett from, I think, like 20 years ago, which argues about this norm being a good proxy for generalization. So this is, I don't remember the name of the norm, though. I think it's just called total weight in your paper, Peter.
It's just, you mean the L1 norm of the parameters?
Yeah.
It's like an L1,
yeah, basically, yeah. I mean, depends how it's just the L1 norm of the sum of like weights of the neurons times the norm of the vector. So yeah, you could think about it as just an L1 norm of the network. And what we show is that basically we give a construction where the norm achieved is the optimal one.
Right. But the implication on generalization of that norm for this specific regime are, unclear. Okay, so
right.
we addressed this question in as I mentioned, what's called the lazy regime, or also the neural tangent regime. And okay, this was first introduced by Jaco, Gabriel, and Hongler. Okay, there are some older papers, but this is really put it to the fore in 2018. And what this means is that instead of the original class of function, I look at a simpler class of function, the NT class of function. This is, depends on a set of weight W. And so this is defined as the set of functions fxa that takes the form sum over I 1 to n, ai times x times sigma prime of wi times x. So these brackets are scalar product, and here this is parameterized by a set of vectors ai in Rd. Okay, so here W, the weights W are fixed. So W is W1, Wn. So these are fixed, and throughout the talk there will be not normal, but they will be uniform on the unit sphere in the dimension. Okay, so so this is another class of functions, is parameterized by n times d parameters, namely only all of these vectors ai, and the wi are fixed and they are not fit to the data. The nice thing about this class of functions, of course, that is linear. Now, a couple of remarks here. There are many things that can be said about this model, but remark number one is that the neural tangent class is a subset of the closure of the neural network class with 2n neurons. Okay, and the way you see it, so basically the neural tangent models are a special case of neural networks, and the way you see it is, for instance, this one. Look at 1 over 2 epsilon. Okay, so look at this construction. This is a neural network with 2n neurons, of course, and you take the limit epsilon to 0, and this coincides exactly with fxa as I wrote above, right? Here the assumption is that so converges, for instance, in L2. Okay, so with 2n neurons, you can basically build an NT model, and this is actually also used in the Bubeck et al. Paper. And a second remark, okay, these will be much bigger. So this means that to prove that there exists a neural network that interpolates the data is sufficient to prove that there exists a neural tangent network that interpolates the data, if I'm allowed to take limits. And the second remark is about computability or efficient computation. And if I do gradient descent in the space of neural network with 2n neurons, with that initialization, of that type, this is well approximated by gradient descent in the neural tangent class. Okay, what's happening here? Okay, so this means that, so for this, there is a lot of references starting in, again, 2010, and I'll just mention Du et al. But there is many more, okay? So all of this paper, and okay, I should mention also Schizaimbach. In particular, Schizaimbach showed that if you scale appropriately the initialization and the gradient descent, you basically converge gradient descent in the neural network model converges to gradient descent in the neural tangent class. Okay, so this is the general type of thing that we'll be doing. Okay, now I'm puzzled because my sorry, I'm having some trouble with my iPad. Okay. Okay, the setting or the type of hypothesis that I look at are the following. The xi will be normal 0 ID. And then sigma will be weakly differentiable with the sigma prime of x bounded by polynomial. And then, okay, the dimension and the number of neuron will be polynomially related. So there exists an epsilon positive such that, say, 0.01, such that capital N is bigger than d to the epsilon, okay? And then I'll add some more hypotheses as results are stated. Okay, so the question in interpolation in this setting is just the question of solving a set of linear equations. And the linear equations are of the form sum over L 1 to N, AL times X, WL times X, I. Okay, so you want to solve this equation in the AL. It's convenient to define a piece of notation. So let me define this map phi from RD to R to the ND. Okay, this is the map that takes a vector X and spits out phi of X. Oh, what's happening? Sorry, I'm having again trouble with my iPad. This is really annoying. I'm sorry, I'm trying to write and it doesn't write. You know, it's kind of frustrating.
Sometimes reconnecting your pen can help.
Reconnecting my?
If you like reattach the pen to the iPad.
Well, the pen is not attached to anything.
Sometimes the pen loses connection with the iPad, the Bluetooth connection. So maybe that's the problem.
The pen doesn't have Bluetooth. The pen or the computer?
No, between the iPad and your, how are they connected, right?
Well, but yeah, that's true. But okay, let's try to see if I can go on. This is so annoying. But the pen shouldn't, I mean, this is just, I'm not writing even independently.
Sometimes you want to check whether the tip of the pen is like tight. You want to go too tight. Can be a problem.
Yeah, perhaps the tip of the pen. Okay.
You want to make sure that's tight. So
Get tight. Okay. Okay, so I managed to write it, except I made a mistake. Okay, so this is the map that takes a vector x and spits out a vector of length nd that has one row of this equation in it. Okay, and so this is this system of linear equation. You can write it in terms of a matrix phi, that is the matrix that has rows phi of x1, blah blah blah, phi of xn, okay, and so this is a matrix that is n by nd, and the set of linear equation is just capital phi times a equal y. Okay, so interpolation means that the set of linear equation has a solution. Okay, and we know that this has a solution exists for most y, and if exists for most, it exists for all y. You know what? I'll try to change pen. Y. If and only if the rank of this matrix phi is equal to n. Okay, so this is the basic question, one basic question that we want to answer. And this is the first theorem that I state. So this is again with Ichao Zhong. And okay, one way to state the theory is in terms of the kernel matrix that is phi transpose. Okay, so this is an n, this is the empirical kernel, is an n by n matrix. Let me define another piece of notation that characterize. So sigma is only characterized through the variance of sigma prime of G. This variance is taken with respect to G normal 0, 1. Okay, and then, okay, we assume there exists C0 positive such that n is less than C0D. And then C1 finite such that if nd divided log n log d to the C1 is less than, is bigger than n, then lambda mean of k is bigger or equal than b sigma minus some small low improbability. Okay, so the theorem is basically telling you that not only, okay, you have to give me some extra log factors, this log n, log d to the C1, but if you give me this extra log factor, not only the matrix phi has full rank, but I have a quantitative lower bound on the minimum singular value of the kernel. And okay, how good is this lower bound? Turns out that okay, if you look, okay, if I have time to talk a little bit about the proof, it's pretty clear that the lower bound is tight, and depends on sigma only if on the variance of sigma prime. Of course, if sigma prime is a constant, that is sigma is linear, then the problem is somehow degenerate. The real, somehow strongest. Okay, we make this assumption about the distribution of the data, but even within the model, the data distribution model that we assume, we have to assume capital N linear in D. This is just a weakness of the proof. Okay, something like this should be true for polynomial N polynomial in D, but I think this regime is already interesting enough. Okay, so corollary is of course what we wanted about interpolation. With high probability for any y. So here y can be generic, of course. There exists A in R and D that parameterize the neural tangent model such that f and t xi A is equal to yi for all I. Okay, so there is interpolation, and since we are in the kind of neural tangent regime, can be found by gradient descent, if at least up to an arbitrarily small error. Okay, so this is about the first two questions, that is where the phase transition is, and whether such interpolators can be found efficiently. There is a third question that is interesting from a statistical point of view, is the one of generalization or test error. In this case, the two coincide. And okay, we study this in a specific setting, that is, we assume a model for y. And more specifically, we take a linear model. So this is, of course, very simplistic. Here, epsilon I are independent random variables and some variance. And okay, so one note, is this very restrictive, this linear model? Yes, but okay, the most general case is not much more general, because if capital N is of order D, as long as we keep to this regime, a model of this type in large dimension can fit. Okay, I should have said from the beginning, but here we are always assume, yeah, N and D going to infinity. Can fit at most quadratic functions. And can fit is in the approximation sense, namely, if you give me a third order polynomial that has 0 L2 projection on linear function and quadratic function, you cannot approximate it to any non-trivial extent by a neural tangent model. Okay, so this is a result that we obtained last year with Gorbani, May, Misakevitz. Myself. Okay, so okay, there is an interesting generalization of what we did, that is go to quadratic function, but beyond that, as long as we keep the number of neurons linear and the dimension large, there is not much to do. Okay, so this is the test error, and okay, here I should have said so. How do we fit this model for studying the test error? We use ridge regression. So we have to fit these capital N D parameters, and we do this by minimizing this cost function. with a ridge penalty. Okay, so this is really, we can also rewrite using the notation that I brought here. This is quadratic cost in the A plus a ridge penalty. Okay, so these are all L2 norms. And okay, and we are interested in studying the test error at value lambda. So this will be the expectation with respect to the new data of the true minus f of okay. Now, why are we interested in ridge regression of all methods? First of all, because it's very convenient mathematically, and second, there is a motivation for it is that if I do in a linear model, so in a linearly parametrized model, if I run gradient descent starting at 0 initialization, gradient descent converges to the min L2 norm solution, so to A hat of lambda equals 0 plus, say. Okay, so if you have least squares and you solve least squares in an overparametrized model using gradient descent and initializing at 0, it will converge to the minimum L2 norm solution. So insofar the neural tangent model is accurate, so you start with this initialization with 1 over epsilon in front of the coefficients, the mean L2 norm solution of the ridgeless limits of ridge regression will capture the generalization error of gradient descent. So I think that the most informative way to state our result about the generalization is as an equivalence or approximately equivalence. And equivalence is with a simple model. And the simple model is just vanilla linear ridge regression. So what is vanilla ridge regression is what you would do if you didn't know anything about neural networks. And you fit just a linear model in the dimensions. With regularization parameter gamma. Okay, and of course I can define once I do this, X is just the n by d matrix with the row xi's. And I can define, of course, the risk of linear ridge regression, let's call it, at gamma. This is okay. Now, this is, of course, an object that in this model is quite easy to study. In particular, you can compute its asymptotics, okay, using random matrix theory. Using just really simple random matrix theory. Okay. Okay, so in particular, there is a paper that we wrote with Trevor Hesty and a bunch of other people in which we do all sorts of these calculations. Okay, so what is the theorem here? Well, same assumption as in the first theorem. So in particular, always n C0D for some big constant C0, and Gaussian data and linear truth. Under this assumption, we have that the risk of the neural tangent model at regularization lambda is equal to the risk of the linear model at a new regularization that I'll call gamma effective, that depends on lambda and sigma, the activation function, plus an error that is of order n log d to the c and d. Okay, so here we're not very careful in tracking the log factors, but okay. And here the effective regularization is what? Is lambda plus b of sigma divided by e of sigma prime, where expectation here is always with respect to the Gaussian measure. Okay, so this is the theorem. You get as good as realization as generalization as if you did just linear regression. The interesting fact is that you don't know that things are linear to start with. So in a sense, you're more adaptive. A couple of remarks here. There is this interesting change in regularization. In particular, even if lambda is equal to 0, so you look at the mean norm interpolator in the neural tangent model, the effective regularization is strictly positive. Okay, so this implies the fact that gamma lambda equals 0 can be optimal. Okay, namely, if you take so one big puzzle here, I didn't go too much into the statistical or machine learning aspects of this problem. I focused here on the math aspects, but one very interesting type of phenomenon that was studied by many people, and is that you get good generalization error with these networks, even if the training error is 0. So lambda equals 0 means training error 0, so interpolation. And this can be the optimal regularization, despite the fact that you're interpolating the data. And in this model is seen very clearly because the effective regularization in the linear model is strictly positive. So you can easily construct models at high SNR. SNR here is basically the norm of beta 0 over the variance of the noise. You can easily build model in which the optimal regularization for ridge regression is small. In particular, is smaller than V of sigma divided by E of sigma prime square. And in this case, the optimal lambda will be 0. Okay. And the underlying mechanism has been studied before, for instance, Liang and Racklin, Peter, myself, etc. But okay, here we see it directly in a model related to neural networks. And the underlying mechanism is, of course, the kernel matrix as this piece that is proportional to V sigma times the identity plus other stuff. And this V sigma on the diagonal from our first year, and this V sigma on the diagonal acts as a regularizer. Second thing, you might ask about the optimality of our theorem. We don't think it's optimal. We suspect it can be improved, but okay, one good thing is that the error term, we don't think that the error term is optimal, but is negligible if n over d is much smaller than n to the 1/3 modulo log factors. And this is basically obtained by balancing this, by comparing these two terms. Okay, the error of linear regression of order lowercase n over lowercase d, and then you balance it with the other term and you get this kind of scaling, if I'm not correct. Okay? So this covers at least an interesting range. Okay, so perhaps I'll pause 1 minute and then I'll go to describe some proof ideas.
Andrea, can I ask a question?
Sure.
If gamma opt is strictly smaller than V sigma over this expectation of derivative squared, you may have an optimal ridge penalty that's negative.
Yeah, yeah. So I must say that there is a simpler model in which you can see all of this, and that was okay. Now I'm blanking. I mean, there is a simpler model for this, that is you just do linear regression in which you add noise to the covariates. In that case, also you can have an optimal. This was studied first by some other people that now I remember, I forgot the name. Yeah, you can have in that model an optimal penalty that is negative, and I think in this model as well. Okay, now I don't know if it's something that I would advise to practitioners, but to do. But in these models you can do these strange things. Okay. A few words about the proofs. Okay, the crux really, as I tried to mention, is try to control the kernel matrix. Okay, so this is an n, matrix indexed by the data points whose entry Kij is 1 over nd. If you remember my definition of phi, sum over L 1 to n, sigma xi xj times sigma prime of wl xi times sigma prime of wl xj. Okay, so it's a bit of a tricky matrix. If it was just the first piece, it would be a Wishart matrix. So if sigma prime is a constant, if the activation is linear, this is just a Wishart matrix. Okay, remind that the xi are random in my model. But okay, here there is this part that makes it. If there was no first part, then would be, if there was no first term, then it would be a kernel linear product random matrix, but is a bit more complicated than that. And the challenge, really, one challenge is, okay, remember that we want to prove that this is basically bigger than this V of sigma times I. And so one might want to try some concentration bound, but it's not true that if you look at k minus any v, any constant v times I, this is much smaller than v. Okay, so it's not concentration. This is lower bounded by a constant times the identity, but it's not because it's very close to a constant times the identity. Okay, so one has to do a little bit more work and identify some large eigenvectors or potentially large eigenvalue. And to do this, what we do is that we decompose, first of all, we decompose the activation function as sigma prime of x equal, okay, we call it psi plus phi of x, where phi, this is orthogonal decomposition, so this is 0. And the expectation is with respect to G normal 0, 1. Okay, and accordingly, you can decompose the matrix phi as phi psi plus phi phi, okay, and these are for instance phi I L alpha. So these are obtained by substituting sigma prime to their components. This is phi wl xi. Okay. Okay, so this is the first piece of the decomposition, and then the second piece of decomposition is that we construct this projector. So this is an ND by ND projector. Where each of the PI, each of the PL is what is WL transpose. And okay, of course, P orthogonal is identity minus P. Okay, so with this in hands, now we write the kernel as first decomposing the part along P and orthogonal to P, and then we decompose phi into the low degree part and the high degree part. This is P orthogonal, and okay, now all of this looks mysterious, but hopefully in a minute it will be kind of clearer why we are doing this. And then we have a last part. Okay, so now what is nice about this decomposition is that this part here is, okay, it's low rank because P is a project of rank capital N, and is obviously PSD. Okay, we want to lower bound K, and so that's good. And now this part is a low degree part. Okay, so let me call it L. And this is really the most interesting part. This is the high degree part. Let me call it K bar. Okay, and what we prove is two things. L, so we have only to deal with L and K. We prove that L is small in the sense that it will be lower bounded by a small constant, possibly negative times the identity, and now K concentrates. K bar concentrate around this V sigma. So this now should clarify why I don't expect, you know, this bound is tight in the sense that, okay, we have this low ranked part, this will not change the minimum singular value, and this low degree part will not raise this minimum singular value either. Okay, okay, last 5 minutes, just one word about you know, these two bounds. Okay, actually only the last bound. How do we prove the last bound, and why reducing to K bar simplifies life, where we prove two by matrix concentration inequality, in particular by Friedman, matrix Friedman inequality for matrix martingale. So this is due to Oliveira and Trop, Oliveira. So it's a matrix concentration inequality for matrix valued martingales, and okay. So what is the martingale? Okay, why is this? Now this matrix is easy to deal with. Let me look at just the out of diagonal terms. and now it should be clear why I impose this constraint, this projector. WL xi projector WL xj times sigma prime WL xi times sigma prime of WL xj. And okay, what is nice, very nice about now here, what I did, this is just the matrix K bar in which I eliminated the diagonal. So I put this indicator here, the diagonal can be treated separately. What is very nice here is that now this piece is independent of this piece, right? Because X is Gaussian, and here I'm projecting orthogonally to the Gaussian. So now these two pieces are zero, are independent. So this, and oh, I should have changed. Now this has zero mean. Remember that I just removed the zero, the constant part psi. I removed from the activation the constant part. Okay, so phi has zero mean, this piece has zero mean, they are uncorrelated. So there is a lot of structure that you can exploit. And the way we construct the martingale is we construct the filtration that is, we condition on all the W, and on the first M of the data points, okay? And then we call, okay, K hat M just the expectation of K hat given FM. Okay, and what is nice about this matrix is that this K hat M is just zero. It's a very simple structure. It's basically K hat ij in the top corner up to entry M and zero elsewhere. So it's very easy to do calculations with this thing and exploiting the independence. And okay, it's not completely trivial, but yeah, you know, with a bit of care, one can get this concentration bound that I brought here. And again, the generalization bound, once you have the bound on the kernel matrix, is basically about, you know, writing explicitly the ridge regression in terms of phi and k, and then approximating each matrix by okay, this should be times identity by you know, using this theorem. Okay, I think that's all for the talk. And yeah, okay, perhaps I could mention that there is you know, a large number of open problems. For instance, here we use a very specific data distribution that is XR normal. Can we generalize it beyond that? I have no idea. Okay, that's all I think. Thank you.
Okay, thank you so much. Are there questions? Someone typed a question into the chat, but you can just unmute yourself to ask.
I was wondering that since the phi matrix has independent rows, is there like a regime of ND and little n where one expects that it will behave like a Gaussian matrix whose with independent rows, whose covariance, the covariance of every row matches the covariance of the rows of the phi matrix?
Yeah, I think so. Yeah, I even wrote down the model. So the question is, yeah, so if you look at a simpler model that is somewhat simpler model, that is, there is a simpler model that is the random feature models. In that case, the matrix phi is replaced by, let's call it phi RF. that is now n by n matrix whose entries are xi sigma of xi dot wl. Okay. In this case, it was shown for this ridge regression problem and conjecture more generally that this matrix phi RF, at least in the proportional regime in which capital N is proportional to lowercase n, is basically equivalent for many purposes to a Gaussian random matrix with the right covariance structure. And yeah, I expect the same to be true here for this model. Probably one has to take ND proportional. Okay, I think there is some work in that direction by Pennington and other, but okay, I think it's true also in this regime. It's a more complicated random matrix model because the covariance has a more complicated structure, but yeah, I think it's true. But yeah, it's probably difficult to prove.
Andrea, in one part of the talk, you mentioned that once you have sigma, even if lambda is 0, the nonlinearity sort of gives you a regularization.
Right.
So is that like, so it's generically true for every nonlinear function, as in are there choice of sigma that give you the reverse of regularization, like it would make the regularization worse?
Well, if you look at this, okay, let's see, where did I write the theorem? If you look at this theorem, really what's crucial here is, I mean, what is this implicit regularization is basically this V of sigma term, and this is the variance of sigma prime, right? So this is always positive. Basically, one way to think about it, I mean, this you see it very easily in kernel methods in IDA. So this you can think of a complicated kernel method in the sense that the kernel itself is random, right? But if you look at a simpler setting that is somewhat simpler setting, so this was studied, for instance, by Liang and Ratlin, and before them by El Karoui and by Als. So the setting in which the matrix Kij is just a deterministic function of xi dot xj, then what happens is that in that case, the situation is relatively simpler, that for two vectors xi, xj in I dimension, so the right scaling is scaling this by square root of d, or no, by d actually. And in high dimension, the scalar product for two distinct vectors is of order 1 over square root of d, so you can linearize the function. But if the two vector for I equal to j, this is k of 0, so k of 1. So kii is equal to the function k at 1, while kij is basically k0 plus k prime 0 over d times xi transpose xj, right? So you see that you have an extra term on the diagonal that comes because of this. So you see the nonlinearity in the kernel only when the 2 points coincide. This is true. This argument is true for, again, n of order d. If you look at n that scales polynomial in d, then you have to look at higher. So you see clearly that this has always to be non-negative, right? Because the diagonal of a kernel is non-negative, right? So here you see it very clearly, and this generalized to polynomial scalings. If you do a higher terms in the expansion, in the you can approximate this by adding higher terms in the Taylor expansion, and basically we are showing the same phenomenon in a somewhat more complicated model, where the kernel is not deterministic because depends on the depends on these W's, okay, in our case.
Andrea, so you're saying that the implicit regularization comes from that diagonal,
yeah,
the extra diagonal. That's what you're saying.
Yeah.
Thanks.
Yeah, it comes from the diagonal. And then, yeah.
So regarding the generalization, if instead of considering a linear model, you consider functions that only depend on one direction, but are not linear, like some nice function that depends only on the scalar product with some vector. Do you believe that, you know, basically the same will hold true? Like
no, the situation, the things will be different, right? So okay, so the question, I don't know who is asking the question. What happens if your function is a, okay, people call it in statistics a ridge function, so it's a g of some W0 transpose times x, right? So now this neural tangent model will not work well, right? In particular, even if you have infinitely many data, you will not approximate well this thing, right? So this is the theorem that I quickly mentioned before. If I take n that is less than, in fact, less than n to the 2, d to the 2 minus epsilon, and you take a function like this, inf over f in the neural tangent class of f0 minus f L2. This is equal to the projection, basically, of this function f0 onto polynomial of degree bigger than 2. Okay, L2. Basically, you cannot, even if you have infinitely many data, you will not approximate well.
But if it's a nice, if G is a nice function, like, I don't know, maybe
What
absolute value, like,
yeah, same true, right?
Or I mean, maybe, you know, supported on small free, like, assume almost anything you want about it. Just, you know, can you say
if you allow me to assume, if you allowed me to assume that G is quadratic, so this theorem, okay,
right?
So this is
not polynomial though, not polynomial.
Right.
I guess.
So this theorem applies to any f0 in L2, and it's an equal plus small order term, right? So this theorem tells you that you know, you can take G as nice. So this is true within the neural tangent model. So this means that if I want to study generalization for this true function, I have, or more general types of function, I have to go beyond the neural tangent model. Okay, so I cannot work in this lazy regime. I'm not saying that, you know, neural networks will not generalize well. I'm just saying that, you know, the machinery that I'm giving you here will not work.
Right.
Does that make sense?
Yeah, it's in the, I guess, in the neural tangent regime, it's pretty limited in that sense.
So Lenk asked the n, capital N here should be lowercase n. No, this should be capital N. This is just an approximation question. You know, there is no model in the neural tangent class that approximates well a function of this type if G is not a quadratic function. And in particular, in general, any function in L2 if it's not a quadratic function.
And
Andrea, of course,
I have a question.
Yeah.
You showed your theorem was lambda min of k greater than or equal to v. So is the v like even the, it's typed like the constant's even correct there?
Yeah.
Like if I had, it's like really the population. If I had infinite with capital N, it would also be V, right?
If I had infinite,
like the
width,
population Jacobian, population kernel, is the lower eigenvalue also V?
is the population where we can.
Like if big N where infinite is the lower eigenvalue also V? Yeah.
I think I knew this. Yeah, I think so. I think
it is?
so.
Okay, cool.
I mean, it's related to the fact that here the limiting factor is lowercase n.
Mm-hmm.
Yeah, I mean, this we are looking at lowercase n by lowercase n matrix, so I don't think that.
Right.
I think so.
Okay, are there other questions? Okay, if not, then thanks, Andrea, so much for the seminar.
Thanks to you guys. Nice to see all of you.
Thanks.
Bye.